So continuing with the describing functions, we'll be now looking into saturation nonlinearity. So as far as the saturation nonlinearity goes, the nonlinear behavior of the system is somewhat like this. The system may or may not exhibit a linear behavior initially, and then saturate. Similarly, in the negative half in the third quadrant. So this is different from the relay that we have done initially, in the fact that the output behaves linearly first with respect to input for some amount of some period of time before being saturated, while as in case of a in case of a relay, the output is saturated from zero itself without exhibiting any linear behavior in any linear behavior. So we are applying the same input, the sinusoidal input. Now we can have two different cases here. One case can be where this output, this input magnitude is somewhat like this, and another case will be where the input magnitude x will be somewhat like this. So here you can see that in the red case, the input magnitude will saturate and accordingly produce a behavior, while as in case of the initial yellow colored input, the magnitude of input is less than the saturation value, therefore it will not actually saturate, and the input output relationship in this case will be simple linear, will be governed by linear equations. And let this angle be alpha. Here we'll be deriving the equation for general case so that we can generalize it for any other case. Fine. Therefore our output here so from 0 to alpha, let me first write this y of omega t. Omega t varying from 0 to alpha. From 0 to alpha, y of omega t will be simply, if this is slope is k here, this will simply be equal to k x sine omega t. So it will only act upon the gain of the input as depending upon the slope of this linear curve, that is k, and we'll get an output equal to k x sine omega t from alpha to pi minus alpha. Our output will be equal to ks, where s is this point here, fine. So this is actually minus s, k is the slope of this curve. So it will actually saturate at s. So beyond this value, whatever is actually the slope, so this, if this is s, the slope is k, therefore this point will be ks. So what we see in case of linear saturation, whatever after this is the magnitude of the saturation, that will be visible at the output as well. So beyond, again, from pi minus alpha to pi, yes, it will again be equal to ks sine omega t. So this will also be equal to ks sine omega t. Depending upon the magnitude of non-linearity, the magnitude of output will also be determined, ks sine omega t. So if we draw this plot from 0 to alpha, there will be a simple sinusoidal curve. From alpha to pi minus alpha, it will be saturated, just like what happens in case of a relay. And then from pi minus alpha to pi, again it will be a sinusoidal curve. So this will continue into the negative half as well. So this here is alpha, this is pi minus alpha, this magnitude is ks. So this curve actually here is ks sine omega t, not kx sine omega t. The magnitude of the sinusoidal curve is ks. So this is our output waveform y omega t. Using Fourier analysis, we need to solve this. Again, looking at this equation, it is an odd function, and since it's an odd function, we'll be finding out b1 for this, and b1 will be equal to 2 by pi integral 0 to pi y omega t sine omega t d omega t. So that is equal to 2 by pi 0 to pi y of omega t is it is ks at 0 to alpha here, ks sine omega t into sine omega t, that makes it sine square omega t d omega t, plus alpha to pi minus alpha, it is only equal to ks sine omega t d omega t, plus pi minus alpha to pi ks sine square omega t d omega t. So these are these are integrals here. So solving this, again, sine square omega t is 1 minus cos omega t divided by 2. So you can substitute that here, then apply the limits. I am directly going to write down the equation. What we'll be getting, 2kx divided by pi sine inverse of s by x, where alpha is actually equal to sine inverse of s by x. Fine. So from alpha, this x is coming into this equation. Sine inverse of s by x plus s by x 1 minus. So you'll have to do some mathematical manipulation. You'll have to divide this throughout by x and find out using this equation for alpha. You will end up at this equation b1 equal to 2k x by pi sine inverse of s by x plus s by x times 1 under root of 1 minus s by x square. Then phi 1 is tan inverse of a1 divided by b1. A1 is 0 here, so phi 1 is again 0. So nx, the describing function for this equation will be b1 by x into angle phi 1, b1 y1 by x into angle phi 1, where y1 is actually summation. It is actually b1 sine omega t again. So substituting that, you will be getting nx equal to 2k by pi where x cancels out with the x in the denominator, sine inverse of s by x plus s by x times under root of 1 minus s by x square angle 0. So this is the magnitude of the describing function along with the phase angle 0. So this is our describing function for the saturation effect. Now we were going to generalize this. So for case 1 where s by x will be greater than 1 or less than 1 rather, that means actually s is less than x, fine. S is actually the saturation effect, that is actually less than the magnitude of the sinusoidal input. That means actually the output will be saturated. So this will be our nx in that case. This will hold. For case 2, where s by x is greater than 1, or you can say s is greater than x, that means the sinusoidal input will never be saturated. So s by x, if we say for example is equal to 1, s by x greater than or equal to 1, s is greater than or equal to x, substituting this here, 1 minus this will become 0, sine inverse of 0 is also 0. So this whole term inside is 0. So this actually means nx is equal to 0. Or sine inverse of 0 can also be pi. So in that case this nx becomes equal to 2k. So in other words, nx equal to y1 by x will be equal to a constant, and in that case, in this particular case, it can be equal to, say for example 2k, and or you can say if k is equal to, say for example 1 by 2, in that case this will be equal to 1 in other words. So it's actually a constant, or it is equal to 1, or in general it will actually be equal to 2k. Substituting for, say for example s by x equal to 1, this is particularly for s by x equal to 1, 1 minus s by x is equal becomes 0, sine inverse, so this whole term becomes 0 here. Sine inverse of s by x can either be 0 or pi or 2 pi or 4 pi. So if we say it is equal to pi, if it is equal to 0, then this whole again becomes equal to 0. If it is equal to pi, in that case nx will be equal to 2k. If it is equal to 2 pi, it will be equal to 4k, 6k, 8k, whatever. So depending upon the slope of the linear curve, we'll be having a relationship between y1 and x. In other words, y1 by x will actually be a constant. So that means y1 will be simply constant times x. That means it's actually a linear relationship with respect to the input. That means input and output in this case will be having a linear relationship and not a non-linear relationship that we see in non-linear systems. So actually our input as well as the output in that case will be a sinusoidal function, whether it's 2k, 4k, 6k, anything. Y1 by x is a constant. That means y is equal to some constant times x. That means y and x are actually linearly related to each other. So that will be a case with the saturation effect. So if our input does not touch the saturation point, it will be having a linear relationship with respect to the input. Output will be having a linear relationship. If the input will be touching the saturation point, it will go beyond that, then there will be a non-linear relationship, and that will be governed by this describing function that we have just derived. Now before we proceed, let's figure out this relationship relation between we have derived the describing function of dead zone nx equal to uh, 2k by pi sine inverse of d by 2 divided by x plus d by 2 divided by x 1 minus d by 2 divided by x square, while as nx for a saturation is again 2k by pi sine inverse of s by x plus s by x under root of 1 minus s by x square nx dz is actually k minus 2k by pi. Fine. So if s is equal to d by 2, for s equal to d by 2, you can simply say nx d by z is nx of the dead zone is equal to k minus nx of the saturation effect. So describing function of the dead zone is k minus the describing function of the saturation effect. So this is a dead zone. This is our relationship between dead zone and saturation. We have done dead zone last time. So number 5, relay with dead zone. dead zone, so when we did dead zone yesterday, in the previous session, what we did was we assumed a linear behavior after the dead zone effect was uh, after the dead zone effect passed. We assumed a linear behavior, but in this case, instead of having an linear behavior, we are having a relay operation, and therefore what happens in this case, if we'll be applying a sinusoidal input, this is say for example d by 2, this is magnitude is m here, and this width is d by 2, so this minus d by 2 x. So if x is actually less than d by 2, then the output will be 0. That's the effect of the dead zone. X has to be greater than d by 2 for any output to be there. Fine. So what will be the how will this output curve look, and how it will be different from the dead zone we have done before this. From 0 to that is actually alpha, and pi minus alpha, this is alpha. From 0 to alpha, our output will be 0. From pi minus alpha to pi, again it will be 0. So between alpha to pi minus alpha, our output is saturated because of the relay operation. That means we'll be simply having an output like this with a magnitude of m. So again, from pi to pi plus alpha it will be 0, then from pi plus alpha to 2 pi minus alpha it will be a curve like this. So this is pi plus alpha, this is 2 pi minus alpha. So y of omega t is equal to 0, is equal to m, is equal to 0, equal to 0 from 0 to omega t to alpha, is equal to m from alpha to pi minus alpha, and is equal to 0 from pi minus alpha to again pi only. So this is our output, and so we can actually apply the Fourier transform on this. The describing function for this curve will come out to be 4m by pi x. This is again a system with odd and half symmetry. 1 minus d by 2 by x square. The angle of 0. So you can apply the Fourier transform of the y omega t that we have just obtained, and using this you can find out the describing function as the fundamental component divided by the input, that is x, magnitude of input, that is x. So you can try and derive this describing function for a relay with a dead zone. So we'll try and derive some more non-describing functions in the next session before we proceed on to the analysis using the describing function. So that is all for the session.